of you who don't know me, I'm Sohini Ramachandran, a faculty member in ecology and evolutionary biology and computer science at Brown, and I'm the director of the Data Science Initiative and the Center for Computational Molecular Biology. And it is my great pleasure to get to introduce our first speaker today, and also just as important to introduce you to the organizers of Fair February, which is a wonderful initiative that has been spearheaded by wonderful trainees affiliated with departments on campus in the Data Science Initiative. And I'm so grateful for their hard work in creating these wonderful events. So I'd like to tell you first about them. I'd first like to say that this was spearheaded in many ways by Dr. Shahrzad Hadadan, who is a postdoctoral researcher in the Data Science Initiative and in the Department of Computer Science. During her PhD, which was done at Dartmouth College, her research was focused on combinatorics and studies of permutations and partially ordered sets. After finishing her PhD, she studied big data and graph mining problems at La Sapienza, University of Rome, and we're really privileged to have her in the DSI community. Christina Mangini is a PhD student in engineering and computer science who is visiting Brown University from La Sapienza, University of Rome. She works in web algorithms and the data mining lab there. She also received her master's degree in data science from the same institution and did work at EPFL in Switzerland during her master's. She has a wide variety of research interests, including digital education, open data, and computational social science. And lastly, Marie Schank is a fifth-year PhD candidate in American politics through political science, and she's also affiliated with the Taubman Center of American Politics and Policy at the Watson Institute here at Brown. Her dissertation explores how everyday political discussions shape political identity with an emphasis on forms of online communication. And in addition to being a PhD candidate, she's also pursuing a master's in data science through Brown's open graduate education program here at the initiative. I also want to thank Professor Seni Kamara and Eliezer Upfall in computer science, because their groups have been very actively involved through these three organizers and also more generally in Fair February planning. And they've been advising this effort. And I also want to mention to you, many of you might have seen other advertisements for Love Data Week, which is coming up February 8th through 12th. So there's going to be a lot to think about with respect to data science and data over the next few weeks. So now what I'm going to do is introduce our first speaker today, Liz Chen. We're very privileged to have kick off Fair February. At 5:10, there will be a second talk by a young researcher, Ruotao Zhang from Biostatistics, who's a PhD candidate, and he'll be introduced before his talk separately. And after I introduce Liz, Christina is going to talk about how questions will be moderated. So Elizabeth Chen, PhD and fellow of the American College of Medical Informatics, is Associate Professor of Medical Science and Health Services Policy and Practice at Brown. She's also the interim director of the Brown Center for Biomedical Informatics. Dr. Chen received a bachelor's in computer science from Tufts University and her PhD in biomedical informatics from Columbia University. She has now been at Brown for just over 5 years, and we're really privileged to have her as a colleague. Before that, she held appointments at Columbia University, at Partners Healthcare and Brigham and Women's Hospital and Harvard Medical School, and the University of Vermont. Her research is focused currently on using data technology and computational approaches for both mental health informatics and pediatric informatics. She leverages a number of methods to analyze electronic health data and health information and communications technology, including natural language processing and many data curation forms and other cutting edge methods in data science. And I just also want to say that BCBI is a very close partner to both the Data Science Initiative and to the Center for Computational Molecular Biology. And we're very lucky to have Liz at Brown and really excited to hear more about her work. And now I'll hand it off to Christina to tell us more about how to ask questions during and after the talk.
Thank you, Sohini. So for the question, they will work like this. So Liz is gonna give her talk, and once the talk will end, we will have a session where I will read all the questions that you can write down throughout the talk in the chat, in the Zoom chat. And if there will be more questions, you can just ask them directly. In the case we will run out of time, you can directly send an email to Liz and have an offline conversation. So I think the stage is yours, Liz.
Great, thank you so much. Thank you so much for that introduction, for having me here. I'm very grateful to be able to give this keynote to kick off the symposium. And I look forward to talking with you about artificial intelligence in healthcare. So the plan for today is just give you a little bit of the history of AI in medicine, talk about kind of where we are with challenges and opportunities for AI in healthcare, and then talk about some of the things that we're doing locally and nationally in using AI to address COVID-19. So let's start with the history of AI in medicine. And so AI goes back to the 1950s, and we've seen how it's evolved over the years. There's a lot of early excitement in AI early on. Some of the early applications were with games, checkers, chess. We then kind of saw over the years, machine learning beginning to flourish, thinking about how do we classify things, do prediction. And then more recently, a lot of attention to deep learning. So how can we leverage deep learning techniques? A lot of this enabled by just the wealth of data, big data, technology advancing, and just a lot of advances in computation. So if we look at this a little bit closer in terms of definitions, artificial intelligence is a broad field, really essentially techniques that enable computers to mimic human intelligence, things like basic logic, if-then rules. Machine learning is a subset of AI, and then deep learning a subset of machine learning. Also just wanted to mention natural language processing as another area of artificial intelligence. We're really focused on text. And so we have a lot of different kinds of data. We have structured data, unstructured data. And so how do we turn our unstructured text data into structured data? And natural language processing is a way to do that. On the right, just kind of showing, the breadth of AI. And so there's a lot of different methods, machine learning methods within that, neural networks, support vector machines, and then a lot of different applications where NLP may be seen as one application, speech, robotics, and just a range of things. And so a very broad area of research and application. So let's look a little bit closer at the history of AI in medicine. And so we can go back all the way to the 1950s when the term was first coined by John McCarthy in 1956. And so we have that highlighted here. And then when did we start using AI in medicine? And so one of the first applications is mycin. And I'll talk a little bit about mycin, who created it, when it got started, and the start of artificial intelligence in medicine. But before we go there, I want to talk about, there's a lot of interest. I mean, this field goes back quite some time, more than 50 years now. And there's a lot of interest back then, but there came this time, you may have heard about the AI winter. So there was a lot of interest, a lot of hype, but then some disappointment, some loss of funding. So we kind of entered this phase of an AI winter, and that happened around the 1970s and 80s. And then there was a lot of push. If we need to be doing AI, a lot of it was maybe due to technology and kind of not being, at the same up to speed. And so we saw more attention to artificial intelligence in medicine, some derivatives of mycin like E-mycin in the 1980s. Part of our history in clinical decision support tools like DXplain. And there was a lot of developments there. And then we had another second AI winter. Again, lots of hype, but then more disappointment, lack of funding, and so forth. And then we have what we have in the 2000s. So I mentioned deep learning. So there's a lot of interest in deep learning. We're seeing a lot of potential there. We're starting to see more applications of artificial intelligence to medicine. We're seeing things like Watson, Alexa, Siri. And so really, again, kind of in this exciting time where there's a lot of promise, there's a lot of opportunities. And the thing we want to be careful of is we don't want to enter another AI winter as has happened in the past. And so essentially what we're in right now is an AI spring. There's a lot of excitement, but we have to proceed with caution. We can really learn from what we've seen in the past. So let's look a little bit at mycin. So this is actually Dr. Ted Shortliff. This was part of his doctoral dissertation. So he developed one of the first applications of artificial intelligence in medicine. So if you go to probably most artificial intelligence textbooks and they talk about the history of AI and some of the applications, you'll see Myson and Dr. Shortliff mentioned as one of the founders or pioneers in artificial intelligence in medicine, and also the field of medical informatics that we now more broadly refer to as biomedical informatics. And so he was one of the leaders in this with his advisor, and kind of developed these books on mice and rule-based expert systems. And so just to kind of tell you a little bit about what Mycin is. And so this was a system that was developed to identify bacteria causing severe infections, particularly blood infections, and recommend antibiotics based on the weight of a patient. It was written in the Lisp programming language and is a backward chaining expert system. So this is actually a graphic from the book to the left about the architecture of the system. And so this is the basic architecture of an expert system, where you have expertise, you have to acquire knowledge from these experts. And so in this case, if-then rules. And so then if you have the system where you can consult, to the Mycin consultation system, you have your clinician users use it using this knowledge base based on knowledge acquired from experts, looking at your patient, looking at their data, looking at this knowledge, and then in this case, answering a series of yes/no questions that then would query this knowledge base to be able to figure out what the bacteria might be and what antibiotics should be given. And then what's also key here that we'll talk a little bit later about is the importance of explaining why the program came up with that response, why they came up with that recommendation and identification. And so having that explanation as part of the system. So Dr. Shortliff, this is a great series of papers that he's written over the years that I highly recommend if they are interested in going into this area of seeing how the field has evolved, some of his thoughts. And so back in 1991, there was a conference on artificial intelligence in medicine. He gave a keynote as part of that. And then afterwards, wrote this paper in Artificial Intelligence in Medicine, talking about the adolescence of AI in medicine, and will it come to age in the 90s? And then in 2007, there was another conference, the Artificial Intelligence in Medicine conference. And then he wrote another paper with also those who were part of a panel at this conference about the coming of age of artificial intelligence in medicine, and really kind of the thoughts on how artificial intelligence in medicine had evolved since 1991. And then more recently, talking in 2019, he wrote the third part of this series about artificial intelligence in medicine, weighing the accomplishments, the hype, and the promise. And again, this is kind of where there's lots of promise, lots of excitement, but just really proceeding with caution. And that's what he kind of writes here is, we're now 50 years old, we're AI in medicine. We've made a lot of progress, a lot of it due to evolution of computer science, hardware technology, communications, and biomedicine. He reflects about how they talked about the adolescence of the field back in 1991, and how it came to age in 2007. And now in 2019, and now we're in 2021, this field is really more visible and it's more influential than before. But then as part of the abstract, he concludes, we just need to be cautious. Again, like in the past, we've had a lot of excitement. We've experienced AI winters. We don't really want to have that happen again. But there is the complexity of medicine and clinical care that we need to take into consideration. And things, when we talk about putting AI into practice, we need to think about usability. We need to think about workflow, transparency. So why is the system behaving the way it is? Safety, and then to have formal clinical trials to assess the effectiveness and the usability of these systems. And so I think it's an exciting time. And so for you who are kind of coming into this field, there's lots of opportunity, but part of this is to kind of show there is a rich history, and to kind of be able to do things effectively now, it's important to kind of know where we came from and all the thought that has gone into this area of research to really inform how we move forward. I thought it'd be helpful to also talk about the history of biomedical informatics. As I mentioned, Dr. Shortliff is a pioneer in artificial intelligence in medicine, as well as the field of medical informatics or biomedical informatics. And so the history is similar to artificial intelligence, where the field started back in the 1950s. We didn't have a formal name back then in other countries. There were things like informatique, informatiki, but now that are more analogous to computer science. But within the United States, we were referring to it as the application of computers to medicine, the application of computers to molecular biology. And in the 1970s, we formally came up with the term informatics. And then at the same time, we had medical informatics, so really informatics more applied to medicine, and bioinformatics is informatics applied to biology. And so these fields essentially started evolving in parallel. In 1980s, we started to see subdisciplines, so things like clinical informatics, dental informatics, nursing informatics. And those in the field in the 1990s said, well, let's kind of fold this under an umbrella term called biomedical informatics. And there is debate about this, a lot of discussion. I won't go into that here. For those of you who take our classes, we talk a little bit about kind of the evolution of the name. But for now, we'll just say biomedical informatics in our community, we view as an umbrella term that encompasses things like translational bioinformatics. So we talk a lot about clinical and translational science these days. And so translational bioinformatics is viewed as a subdiscipline that really focuses on bench to bedside, and clinical research informatics really thinking about clinical trials and the data and the techniques we need to use to support those. And so biomedical informatics is this umbrella term that includes things like subdisciplines of translational bioinformatics, clinical research informatics, public health informatics. And we've done studies. This is actually a study where we found there was almost 300 subdisciplines of informatics out there that fundamentally the methods are the same, but how we apply them may vary. So here's a formal definition of biomedical informatics. And again, I bring this up because artificial intelligence is a big part of what we do. We're a highly interdisciplinary field. We take methods from computer science, math, engineering, domains, biomedicine, clinical medicine, public health, bring them all together. And really our goal is to effectively use data, information, and knowledge with the ultimate goal to improve human health. It's a broad discipline. We go from molecules to populations. And so this is a graphic that kind of shows that and all the subdisciplines and how they fit together. We really grounded in theory and methods from a range of the fields that are kind of the primary disciplines that make up this field. Technology is key to what we do. And we really need to take into consider human social context. So if we want to build new systems, AI systems, we really need to understand, draw from the social and behavioral sciences. And so bringing all this together, we do this in the field of biomedical informatics to really come up with solutions to improve human health. So let's kind of fast forward. So we talked a little bit about the history, but where are we now? And so in 2007, we started hearing about the learning health system. And so the concept is not necessarily new, but the term has become, what we're using these days of thinking about how do we go from data to knowledge, then knowledge to performance or practice, and then practice to data. So look at what can we learn about from data. So that could be electronic health data. Whatever we learn, how can we put that into practice? Can we put that into practice through clinical decision support? Then how do we know that's working? So we're collecting more data to see, is that particular tool working? And it's this learning cycle. And so what we call it is this continuously learning health system, informatics being key to it, to really kind of enable a learning health system and really kind of having this translation between research and practice. So also, again, if this is an area that you're interested in, there's a lot of different books in this series. They talk about different aspects about the data pieces of it, the infrastructure that we need to enable a learning health system, the data, the technology, all the things that go into it. And one of the more recent reports that have come out of this series is one focused on artificial intelligence in healthcare, the hope, the hype, the promise, and the peril. And so that one came out in 2019, and I'll actually, the second part of this talk will be delving a little more into this report. And again, recommend if this is an area you're interested to kind of go through this. It talks about a lot of the challenges and opportunities in AI and healthcare. And it, again, kind of what Dr. Sherlock had talks about in his papers is there's so much potential for AI. It can be transformative to advance healthcare, but we really need to be thoughtful and not have unintended consequences, marketing hype, and profit motives. And so really we have to think about a lot of things as we put AI into practice, with the ultimate goal that we could help achieve the quintuple aim of improving population health, improving the well-being of care teams, improving the patient experience, ensuring equity inclusion, and then also reducing costs. And here we'll come back to this life cycle, but as you can see, all of these, there's just many components to it. And so for those of you who are kind of, training in this field, you may kind of be part of one piece. So here you may focus really on the data to knowledge. There may be others really focusing on how to put that knowledge into practice, or you might kind of know a little bit of everything and try to do this whole cycle. And that's a little bit about what we'll be talking about for the rest of this talk. Okay, so now let's jump to some challenges and opportunities for AI in healthcare. So lots of opportunities. We're seeing AI in a range of contexts in healthcare. We're seeing it using to help the diagnostic process, for finding anomalies in medical imaging, helping find new drugs and treatments, looking at ways to study how hospital information systems are being used, how can we better support care, seeing it used for research that can be used to inform care. We're also seeing AI in wearables and watches and other applications, virtual assistants, and then we're also seeing it in specialty areas. So probably any clinical specialty you'll see, there's some paper written about how we could use AI to improve nutrition, mental health, workflows in the emergency department, in surgery. And so really lots of potential, lots of ways we're seeing AI being applied in healthcare. And so what are some of the challenging opportunities? So there's a lot of them, and this is a broad field, and there's only so much we could cover in one talk, and there's so many areas that we could go into. So what we'll be doing today is really just trying to give you kind of an overview or a sense of what's going on in the field. And so again, this is tied to that report, Artificial Intelligence in Healthcare. They actually then ended up putting together a JAMA article on this. And so these are some of the things that they highlighted in that, that this report addresses. Is we want to promote population representative data. So we don't want just data. We need to make sure if we're addressing a particular clinical or health question, that the data we have represents that population. And of course, as you may know, with working with data, there are always issues with accessing data, standardizing data, data quality. You want to make sure if you develop models, the data are good. And oftentimes they're not great. And so thinking about, knowing your data well and taking that into consideration and maybe potentially seeing if there are ways to make the data better, the way it's collected at the point of care, there's a lot of opportunities there. Other things is, there's always going to be bias in data. And so thinking about what the potential biases may be and making sure that we prioritize ethical, equitable, and inclusive healthcare AI while thinking about these issues of bias. We talked a little bit about transparency and trust. And so we don't want that black box. We need to know why a system is operating the way it is. And so there's a lot of attention now to making sure what we're finding is trustworthy, and also there is transparency so that we understand what's going on. The fourth bullet, near-term focus is needed on augmented intelligence. So I think this is a really important part. We've been talking about this in the informatics field for some time, back when we used to call things clinical decision-making. And then we were very careful to say, well, it's clinical decision support. We don't want the computer to be making decisions for clinicians or patients. They should be augmenting it or supplementing it. So now we refer to it as clinical decision support. As we're trying to support, we're not here to replace clinicians or patients or others involved with healthcare. And so this is what the fourth bullet tries to address, is not necessarily autonomous agents, but really augmented intelligence to help you make decisions for your care. On the right-hand side, I think this is particularly applicable for this symposium is, we need more individuals trained and educated in informatics and data science. There's so many challenges to address, so much potential, so many areas we can use it, but we need more people doing work in this space. There's a lot of frameworks out there. We don't have to reinvent the wheel. And so being aware of what the frameworks and best practices are for learning healthcare systems, for methods that are out there, thinking about things as we put things into practice, we need to start thinking about social and factors, human factors, what's a thinking process, and also implementation science as we think about operationalizing healthcare artificial intelligence. And the final bullet point is also very critical is, we can innovate, we want to build these models, we want to build these AI applications, but we really need to be thinking about safety through regulation or legislation to promote trust. And so I think these really highlight some of the things that we need to be thinking about as we kind of embark on our journey to do artificial intelligence in healthcare, whatever part it may be. And so this just shows, here's the report, and then here are the different chapters that really go into more depth of each of these. And again, there's so much to cover, but I'll try to cover some aspects of these as part of this talk, and then also talk about some of the work that we're doing in this space. So transforming to data to knowledge. So we talked a little bit about frameworks. And so some of these may look familiar to you, but this was a picture on the left is from early on from AI magazine in 1996 about this knowledge discovery and databases process. And, how do we go from data to knowledge? And so there is a process of, getting your data, selecting your data, cleaning your data, transforming your data. Most of the time it isn't in the format you need to do data mining or machine learning. And for those of you who have done these studies, probably can confirm that most of the work is here. It's hard to get data. There's always data quality issues that need to be addressed, cleaning it, transforming it. And so we oftentimes will say, and when we teach our classes, 80 or 90% of your time will be in this phase. And then once you get it in the right format, whatever your favorite data mining technique or machine learning method is you can apply that. We get the results and then we have to interpret them. And then that also is a challenge is what does it mean? And then if you think about, oh, we have to put this into practice, well, what are the implications? And so there's a lot to think about as you go past knowledge into practice. On the right side with data science, there's analogous workflows. And so if you see, it's basically the same as the knowledge discovery and database. The words are a little bit different. The technologies are different as well. Some of these didn't exist back in the 1990s. And so we're actually seeing, a lot of things evolving as technology has advanced. But same concept is we need to collect our data. We want to explore it. There's lots of great tools out there. We need to munch the data and then we can model it. We want to validate or evaluate it and finally report it. And then kind of take it to the next step of actually how can we actually use that knowledge. This is a kind of adaptation of those two workflows. And so this is what we've applied to health data. And so very similar and kind of going a little deeper. And so there's a lot of data in the health domain, including the EHR, the electronic health record. These data oftentimes will go into what's called a CDR, clinical data repository, and then sometimes will get integrated with other types of health data in enterprise data warehouse. But the same thing, depending on what your study, how do you define a cohort? And what's the phenotype, and thinking about those things, who's your population? Who do you actually want to study as part of your work? And then getting their data. And as we talked about early on, some of it's structured, but a lot of the data in healthcare as well as other domains are unstructured free text, and you need natural language processing. You can then use NLP, turn it into structured data, merge it together, transform it, and finally, when you get to the part of data mining, you can then start looking for patterns. You can come up with predictive models, and then similar to the diagrams before is then it turns into knowledge and then wisdom and kind of thinking about how do you actually put that into practice. Big data. So we've heard a lot about big data, started with 3 Vs, then went to 5 Vs. And so this one is now up to, I guess, 10 Vs. And I think there's actually even more Vs out there. But I think it shows you the complexity of data. And we talked about some of this already. There's different kinds of data, so lots of variety. We have structured data, we have unstructured data. There's lots of data coming with, all over the place. How do we know the data are accurate? How do we know they're useful? On the right side, data will change and there may be different heterogeneous data coming. So how do we actually bring them together? And this is where things like data models and semantics are really important, is how do we actually have common data models, semantics, so that when we get things from multiple places, we know they mean the same thing. And then there can be vagueness. So there's a lot of issues that need to be addressed before we can actually analyze our data. Within the healthcare context, we talked a little bit about electronic health records already, but there's a lot of other sources of data. So from wearable devices, research studies, patient portals, you could study one or you could study multiples of these, and kind of as you add more, it becomes more complicated. On the right-hand side, also just to kind of show a little more in depth, there's lots of different types of data, even within electronic health record. Some of it's structured, and so things like diagnoses are structured, and there may be a standard like ICD, the International Classification of Disease, that may be associated with these. So you essentially have structured and coded data, but you may also have a lot of unstructured data that have a lot of information may only be captured in text. And so needing to have techniques like NLP pull those information out and standardize them in some way so that you could combine it with ICD codes for a diagnosis. So this kind of gets to, data standardization. It's really kind of critical. It's one of the kind of key first steps. Again, I oftentimes will say not the most exciting, but really critical for kind of the downstream analyses. So this is also from that report, that AI in healthcare report that I mentioned. And I thought this was a really nice graphic that shows we have all these different kinds of data. So these different data generating sources, and the shapes kind of show, look, they're different. And so we have electronic health records, we have patient generated data, administrative data, there's other clinical data that might be already standardized, and then you could have publicly available data sources. And so how do we actually make them talk to each other? And so you hear a lot these days about standards and interoperability, and that's what that's really getting to, is you need to have common data models. And I'll talk a little bit in some examples of some of them that are out there. And so you can kind of see, okay, now that all the shapes are squares, because now they're all in the same structure, they're talking the same language, and then you can combine them into a flat file. So, and then give it to your favorite AI algorithm or your multiple AI algorithms, and to do comparisons. And so really, if we want to really promote AI, we need high quality, transparent, and interoperable data. This picture on the right kind of gets more into the natural language processing and how a lot of information is in text. And so there are a lot of NLP systems that are out there and standards. I talked a little bit about ICD that's used for diagnoses, but there's also medications, symptoms. They may have their own different terminologies. And so what's been developed at the National Library of Medicine, at the National Institutes of Health, is a system called the Unified Medical Language System, really a meta-thesaurus that tries to bring together code from these terminologies together. And then some of them, in some cases, will map to each other. Some of them will have one-to-many or many-to-many mappings. But again, there are standards out there. And so this is part of getting to what I was talking about on the other side about best practices and frameworks. There's a lot out there, the lot that the AI in medicine and informatics community have been developing over the years for decades. And so these are things that can be leveraged to turn free text into structured data and be standardized and be able to support AI development through the standardization. For those of you doing machine learning, there are many different models out there. So, there's unsupervised learning, so things like clustering. So in a health context, you might be studying a particular population and want to see if your patients cluster in some way, if they form subgroups, and really understanding why they're forming those clusters. On the other side, supervised learning, things like classification. If you want to develop predictive models, you want to predict, is a patient, will that patient have a particular complication, the mortality? And so there's just a range of things that can be answered with both supervised learning, unsupervised learning, and then also reinforcement learning. And so just a range of techniques that are out there. On the right, this picture tries to show on the scale of, we talked a little bit about, humans and computers. And so this tries to show different kinds of AI applications, and those that may involve more humans and those that are completely, I think as the one on the previous slide, autonomous. And so we really want to augment the human. So somewhere in between here, rather than replace the human. But this kind of shows what the different methods can do, and then the scale of data. So for deep learning, we need larger data. For some of these more human-based systems, so like here we say number 22, clinical wisdom. So, based on a provider or clinician's experience, other similar cases, they can kind of, and literature that's out there, come up with decisions. Here you actually see mycin, so number 14. And so that's how you have the computer system really trying to supplement or augment the human and having knowledge based on some expert knowledge. And then as we go along here, we see classic machine learning. And so we see somewhere here, it's kind of the balance between the human and the computer, needing some techniques, needing more data than others. And then finally up here is having the computer and really the deep learning approaches somewhere along here, again, needing more data, and then having less human to machine decision-making effort. And so this is where we start talking about things like the black box issue, is you don't know why the computer is making those decisions. So that kind of ties into what we're now seeing for an area called explainable AI, really wanting to be explainable and transparent. So here's where we are now, is we're entering a new age of AI applications. Machine learning is the core technology, But one of the challenges is that machine learning models are opaque, non-intuitive, and difficult for people to understand. And this doesn't just apply to medicine and healthcare, it's just really any domain. And so I think this is a really nice graphic from DARPA that kind of shows some of the issues. Is you have this great AI system built from data that we have, but then on the other hand, when we think about putting it to practice, the user is saying, well, why did the system do that? Why didn't it do something else? When are you going to be successful? Are you going to fail? Can I trust you? And then how do I correct the error? And so again, the National Academy of Medicine report, it's part of it, talks about different kinds of transparency. So there's different kinds. One, explainability. So how does the algorithm reach its results? And so that gets into the questions of, when we looked at mice, and one of the big components was the explanation facility is, it has to give some kind of explanation. So there's a range of techniques that are being explored now in Explainable AI to be able to give some insights to what the models or algorithms are actually doing. Other things that I think really tie into what we keep talking about now, open science, is data sets. So where did the data come from? So if I'm looking at the electronic health record, where did the data come from? How was it processed? We talked about that whole knowledge discovery pipeline of we have to clean the data, but we have to have insights. We have to know what was done so that we can actually trust the results. The same thing, how was the algorithm developed and validated? And so knowing, what models were used, if there were tweaks to it, what happened, a lot of these techniques requiring adjustments of parameters and different variables. And so really having insights to what was done at the modeling step. And then finally, the architecture, as we kind of see, there's many different pieces to systems and lots of pipelines for AI and healthcare being developed out there. Just knowing their key steps and how they fit together. But this is another important step, is really understanding how do the pieces of the AI system work together, again, to give more as a form of transparency. Kind of now thinking about, the balance between the model. And so now we're kind of going into, let's, thinking about how to put into practice. So these are some examples of AI applications and thinking about who are the different stakeholders, what are different tasks. And so we think about in the healthcare domain, we have payers, we have patients and caregivers and providers. Some of the tasks we may want our AI application to do is help with diagnosis, help with prognosis, prediction, or treatment. And here are some examples. And so if we kind of look at this one is, we want to develop an AI application that estimates the risk of post-surgical complications. So helping with a prediction task, and really our target are patients and caregivers. And so some of the things we're going to think about when we're actually developing the models or the machine learning models is what's the downstream intervention? So, what's this going to look like in practice? And so is it going to be a clinical decision support tool in electronic health record? Who's the target user? And so in this case, we said, okay, it's the patient and the caregivers. What are the mechanics of executing intervention? So how is that actually going to work? And so this gets more into the implementation of things. What happens if it fails? What if there are adverse events? And thinking about those things. What's the capacity to intervene given existing resources? What accuracy is needed? And so this is oftentimes things we'll talk about as part of evaluation field of these applications, is balancing false positives or negatives. And depending on the context, you may favor one over the other. So is it okay if it's wrong, or is it okay if it misses things? And so these are things to kind of think about in the evaluation phase of the models, as well as when you put them into practice and when you're doing evaluation. And finally, what's the desired outcome change following intervention? So in this case, the ideal thing is that if you put this AI application to practice, will reduce post-surgical complications. And so again, lots of things to think about, but just wanted to provide this as an example. And then also now thinking about deploying AI in clinical settings. And so we talked about, building these models. We talked a little bit about things to think about as you're doing the model development. But now we're getting to, okay, when we're going to put this into practice, what's that life cycle? And so we're coming back to this figure that we saw early on of identifying needs. So do we actually need this AI application? If we do, we have to understand the workflow. So where does it fit into workflow as clinicians are interacting with the electronic health record, or when patients are interacting? What's the desired target state? We can acquire a system, so we can build, or we could buy a system. And thinking about integration issues, we can implement the AI system in target setting. And again, this will vary depending on what you're doing and where it's being implemented. Big part, monitoring how it's working. You don't want to just put it in. You have to make sure it's working as expected. And of course, this ties very similar to the software engineering process, is maintaining, updating, and sometimes de-implementing. So if you find that it's not working well, you sometimes will have to de-implement it. And again, same thing like the learning health system is, it's a cyclical process. And I won't go into this into detail. There's a lot of different challenges, but we talked a little bit about how you have to understand workflows. We talked a little bit about explainability and transparency. And so really, if you want to put this into practice, things need to be explained to really be augmenting practice rather than replacing. Education is a big part of it, oversight and regulation, engaging your stakeholders, engaging clinicians and patients. And again, we talked about this, about data quality and access. And so really, that's really critical, because if you build these tools on bad data, it's likely the intervention will not be great as well. And so really understanding some of the data quality issues and being able to get to the data that's needed to actually build effective AI applications. I think this is the last slide in this section, but just thought this was a nice kind of graphic that summarized all the things that we talked about in this part of the talk. And so this is actually by author for several out in Stanford that talks about, it's really a multidisciplinary process for creating, implementing, and evaluating AI-enabled systems for healthcare. And a lot of these things we talked about is really needing to understand the problem. If we're working with electronic health records, we need to analyze the data to study the process. Designing the intervention involves working closely with the stakeholders, oftentimes doing qualitative methods, focus groups, interviews, understanding how they work, what they need, designing the process workflows, and also in parallel developing these machine learning models that we've been talking about. Then implementing, we really have to think about the culture, organizational issues. We want feedback. And then there's a training piece of this. And then finally, evaluation. We want to make sure the implementation is working well, the process is working well, there are good clinical outcomes, and also monitor the performance of the machine learning, which may change as you get more data. As clinical practices change, we'll have to be updating our models. And then kind of going through the process again. And what I thought was really nice here is it says, again, it's multidisciplinary. We need to take methods from process improvement, design thinking, data science, information technology, and implementation science. And then expertise comes across different disciplines. So we talk a lot about team science, and really this involves team science of members from different disciplines, from those in user experience design, data science, healthcare operations, clinical informatics evaluation, and ethical integrity assessment. So I'll kind of close this part of the talk with this picture that I think nicely summarizes kind of the overall process and kind of what's needed to actually do these implement these AI-enabled systems in healthcare. Okay, with that, we've talked a little bit about the history, some of the challenges and opportunities. Hopefully you can get a sense there's a lot of opportunity, but also a number of challenges, and also why we need more individuals trained in this area to kind of help realize the vision of AI in healthcare. So let's talk about a couple of examples that we're actually working on. So within the Brown Center for Biomedical Informatics, we're engaged with a number of COVID projects. Just thought it might be helpful to give a little bit of background of what BCBI is. And so as Sohini mentioned, we've been here about 5 years. And so the center is a little over 5 years old now. And we really, our mission is to innovate how data and technology are used. And so going from data to knowledge, implement solutions, so that knowledge into practice. We want to make sure we're making an impact and inspire. And so training and education is a really big part of what we do within the center. We have faculty here, so our core faculty doing ranging from molecules to individuals to populations, doing work with artificial intelligence and evaluation. We're teaching classes that kind of cover all aspects of informatics, including artificial intelligence, and looking at systems and providing broad views of the field. And here I just wanted to highlight, we talked a little bit about how it's hard to get data. And so one of the signature initiatives that we've been working on for the past 5 or 6 years is what we're calling the Unified Research Data Sharing and Analysis Initiative, the URSA initiative. And this is really tied to the service role that we have within the center, and that's particularly through advanced clinical and translational research, or advanced CTR. And so BCBI, we operate the advanced CTR Biomedical Informatics core. And so one of our roles is to help researchers get access to data. And so what we've been working on are making a lot of the arrangements that we talked about earlier in the talk, legal arrangements, technical arrangements with our hospital systems, with our health information exchange system in the state, our all payer claims databases. These are just a few examples of data, health data that are out there, and being able to analyze it in a secure environment. So at Brown, we have the Stronghold Secure Computing Environment. We have a portion of that here that's associated with the NIC initiative that we call URSA Stronghold. We have workstations in there for Windows and Linux. We have open source software. We have databases, and this is through our arrangements with some of our health data partners, and they're all in different phases. We're able to generate data sets here, de-identify them, and bring them over into the Stronghold environment to do just a range of analytics, machine learning, deep learning, statistical approaches. So just a range of different analytics, with the goal that at some point when we can learn from these data and then kind of start thinking about the AI applications that could be implemented based on our findings. Just a little bit of background to what EHR and HIE systems are. So the electronic health record is a longitudinal electronic record of patient information. So if you go to a hospital, they may have an EHR system, and that's where every visit you have, they'll collect information like your demographics. They may have notes, problems, medications. The goal of EHRs, there's a big push to implement them nationally, and so we have them pretty widespread at this point. So again, that's kind of contributed to our volume and velocity of data. Is really, they try to automate and streamline the clinician's workflow. But in the context of here is we can view it as the data that we're collecting in the EHR can be used to help support evidence-based decision support, quality management, and outcomes reporting. And so if we think about the EHR, you're at a particular setting, you may have one EHR system, but think about if you actually go between different systems, either within a state and even as you go across the country, but how do we actually connect those pieces of information together? And that's really what a health information exchange does. And so we may say, okay, we had a hospital visit. You also visit your primary care physician. They have two different EHR systems. There are mechanisms for sharing data between them, but there are also health information exchanges which can actually bring together information from these different sites for a given patient and really create that whole longitudinal view so that you don't get gaps in your data. And so really standards are fundamental to how making HIEs work, interoperability, and really being able to create a longitudinal view. And so within Rhode Island, the Rhode Island Quality Institute operates our state's health information exchange, which is called Current Care. If you're interested in learning more, there's more information in this guidebook that can be found at this link. And so Current Care has over half the state's population enrolled. It gets data from over 500 data sources, so electronic health records from healthcare systems, from pharmacies, from labs, just a range of data sources across the state, all come together within the Current Care Health Information Exchange. And for clinical purposes, care teams can see patient data using what's called an application called the Current Care Viewer. And so really not just seeing data from one healthcare system, or really a whole range that a patient may have visited. And patients can also view their results by going to something like Current Care for Me. So looking at kind of, how can we use this EHR data, and kind of going back to the frameworks we talked about earlier in the talk, is how do we turn EHR data that may be in an HIE like Current Care into clinically actionable knowledge? And so this also graphic, also from a book that Dr. Shortliff and Dr. Simeono edited. Here's a graphic from that book that kind of talks about, you have EHR data. We can analyze those data for biomedical research. We can create registries that may be kind of disease specific or focus on particular populations. We can apply different analytic techniques, so different AI approaches, to come up with new standards of prevention and treatment, come up with new guidelines, and then use that to put into practice new AI applications. And then at the point of care, hopefully improve providers caring for patients. And again, this may look similar. The learning health system is we keep collecting more data, we learn from it, and we put new interventions into practice. This is another graphic that kind of is similar, but shows a little bit of a different perspective of this one on the left. And this is tied to the National COVID Cohort Collaborative that I'm actually going to talk about in a little bit. But again, we have patients coming to patient encounters. We're collecting their data from the electronic health record. This can go into databases or registries. We can make inferences using just a range of techniques gain new knowledge, manage that knowledge, guidelines coming back to MySIN, put that into an expert system, and put that into practice through expert systems or decision support. And what I thought was nice about this graphic, it really talks about, the importance of standards and interoperability. Is we have to have common data models. So if we want to do work over different kinds of data sets and integrate them, we need common data models and also terminologies. And so really standards are fundamental to making any of this work well. So some of the projects where we have 4 active projects right now that we're working on within BCBI and Advanced CTR in collaboration with many of those across Brown, as well as our healthcare partners, our health data partners. And so just to kind of give you a sense of what we're doing, we're doing some information retrieval and graph mining techniques applied particularly for symptom monitoring. We're also involved with projects focused on improving testing in certain populations. In this case, part of this Radix Up initiative from NIH for the Latinx population. So we're really doing a combination of qualitative and quantitative methods to be able to study, in this case, our stakeholders, our providers and patients, understanding the barriers to testing, what their thoughts are. We're going to be analyzing data and then putting those together to see if there are ways we can come up with interventions, whether or not they may be automated or they may not be automated, but looking at that to improve COVID-19 testing. 2 others that I'm going to talk a little bit more in the next few slides is this one called the National COVID Cohort Collaborative. And then also what we're doing locally, so funded by a SEED award to create a learning health system in Rhode Island for COVID-19. So N3c, there's actually kind of, if you think about it, there's 2 parts of this. One is data standardization and sharing. So the goal of the N3c initiative from NIH is really, I think summarized well here, is to create the first nationwide patient-level data set in a certified secure environment. And so what they've done is they're partners nationwide. So many different sites across the countries are assembling data related to COVID-19 and sharing it with this initiative with the goal that it'll help us better understand COVID-19 and then help us kind of think about ways we can address it. One of the challenges I talked about is we may have non-standardized EHR data. So the focus is really on EHR data. So things we are talking about is phenotyping. So how do we identify who are the patients who should be included in the data, acquiring that data, and then data ingestion and harmonization. So really there's a couple of common data models out there. So a lot of acronyms here. The one we're focused on is OMOP. So I'll talk about that one in the next slide or 2. But looking at how do we actually map it to a common data model? Because as you can imagine, if we're getting data from all these different sites, they can be in different formats. So we need to standardize it to a common data model and bring it together into a centralized location. So they've created what's called a secure data enclave at NIH that they're bringing together data nationally. And here are some statistics on what's in the database right now. And so as I mentioned, OMOP is the common data model, the target one. So there are other data models that are out there, but we're all working on mapping it to OMOP, either at the site or once it comes to the enclave. There are 39 sites who have contributed so far with over 2.7 million individuals, over 500,000 COVID cases. And then these are some of the other data that is available for those cases. So things like clinical observations, lab results, medications, procedures, and visit information. So that's one part of it, is really, we need to standardize data if we want to share it. And so there's a big effort to actually share the data. And so we're in the midst of working on that right now. And the other part of it is, with all this data in this secure environment, we can now do machine learning, statistical analytics on patient level data. And so of course there is a process. You need to be authorized depending on the type of data. You may need IRB protocols and things like that, but really to bring it together so that we do this effort in a collaborative way. And so really it's a national effort. We're working together to bring data from our sites into the centralized environment. And then together, they've created these domain teams. There's a lot of different clinical domain groups, different questions that are being asked, bringing together that we can work together across the country to address different questions in this area. And so they've created this environment called the N3c Data Enclave. There are a number of tools in there. The primary ones are R and Python. They're also using Apache Spark and also a tool called Contour to do some exploration. And they're also working, one of the efforts is to create synthetic data. And so that's another effort as part of this initiative that we're engaged on. So we're working on contributing data. We're starting to get trained and educated on using this analytic environment. And so that's one of the things, if you're interested in working on this as a student or just someone who's interested, feel free to reach out. But it's a work in progress, and we're kind of just everything's just a work in progress at this point, and we're kind of making progress with contributing data as well as starting to use the enclave. And I know I'm out of time, but this is getting to the last few slides, but that's kind of what's going on nationally, but what are we doing locally? And so it kind of ties, yes.
You have a couple more minutes.
Okay, great, thank you. What are we doing locally? And so it kind of ties hand in hand. And so what we're working on is the data that we're working on contributing to N3c is from RIQI. And so we're in the midst of doing mapping to that standard I mentioned called OMOP, which is the Observational Medical Outcomes Partnership. And so running into a lot of interesting issues, as you can imagine, a data source that has so over 500 data sources contributing into it, dealing with a lot of interesting standardization issues. There's another data model out there called I2B2 that some of you may have heard of. I2B2, it's another data model. There's actually another initiative called 4CE that's looking at data and collaboratively working together, and that's an international effort. And they've taken a different model of, rather than contributing data to a centralized location, is to be able to have common tools. And they believe there are tools that you can bring locally and to run on your data set. So we're working on engaging with both. But the first step is to get the data, standardize it to both OMOP and I2B2, lots of initiatives and tools out there that we can use. And similarly, the goal locally is that we're going to start delving into the data set. Once we have it in a standardized format, there's lots of tools that we can use for analytics. There's a set of tools from an initiative called Odyssey, which is the Observational Health Data Sciences and Informatics. Most of the tools are R-based. They have a lot of GUI-based tools that we can do analytics. And so we're looking at that. But also we've done some development. So particularly our medical students and MD PhD students have been developing PredictMD in the Julia programming language to do different machine learning techniques. And so we can do clustering, classification, do some association mining, sequential pattern mining, just really try using a lot of different techniques on these data to answer a range of questions. And then with the goal of ultimately that we'll be able to gain knowledge from the data that we have locally and then figure out how do we put that into practice, and really thinking about what the stakeholders need, whether or not they're patients or they're providers. In the context of RIQI, they have a number of applications. So seeing how what we could do that we learn from these data, how can we put into practice to actually improve both kind of the patient care as well as patient care. And again, a lot of technologies that I don't think we have time to go into, but a lot of tools out there, smart on fire that you may hear about. But these are kind of things as you start thinking about putting things into practice in the applications. And so really kind of doing the AI enabled system of, we go from our data and then how do we put into practice. And so we're really kind of in this phase. And so again, lots of opportunities to work together if you're interested, and with the goal of that, we'll go through this whole pipeline and kind of relating to what we talked about early on the talk. So with that, I think this is my last slide. And I thought, again, this pulls it together pretty nicely. There's another report from the National Academy of Medicine talking about artificial intelligence in health settings outside the hospital and clinics. So hospitals and clinics are just a third of the picture. The rest of it is, when we're at home, when we're at work, when we're in a community, there are different roles of AI. And so I think we're probably seeing there's AI everywhere. And so there's a lot of opportunities there. But again, I think this kind of summarizes, the things that we need to think about. There is the applying different techniques to data, learning from the data, but we need to think about our stakeholders, what are we developing these applications for, being thoughtful about the design and development, making sure we're developing tools that make sense and that are thinking about the end user and existing workflows. We need to make sure we do really thorough evaluation and validation. So make sure we assess clinical and economic utility of any tools that we put into practice, and that we make sure we integrate them into routine operation, encourage broad adoption. And that really means understanding our stakeholders, understanding workflows. And then finally, the ideal scenario is that what we develop is generalizable. What we develop here in Rhode Island could be used elsewhere, and what we develop for one healthcare system could be then potentially expanded to others. And with that, I thank you, and I'll stop there.
So thank you very much, Liz, for this very interesting talk. It really gave an overview about the AI in healthcare. So we still have a few minutes. So if there are questions, we can take them now. So you can just unmute yourself and speak. Okay. So if there are not, I can have a couple of questions. So they are more related about how much these tools that have been developed are adopted by the communities of doctors. What you just said in the last slide is that we can differentiate among tools that directly work with individuals, like when we are at home and we are at work. And then we have those that are provided to the medical community. And so my question is, which is the community that is more responsive? So individuals, or what about the doctor community? How are they responding to these tools that you are proposing?
Yeah, I think there's a range. I mean, I think that's, there's a whole range of applications, and I think that's, it ranges, which ones are adopted or not. And I think that's part of what we're talking about, is really understanding the needs and engaging them early in the process. So it's not just about developing a tool and saying, okay, the tool's implemented, now using it. Part of the adoption process means, user-centered design and taking the end user, keeping the end user in mind. And so part of the learning system, they say, before you even get started, you should have what they call, I think, a learning community. Is, whether or not it's something for individuals, even that, requires working with individuals who may be using these applications at home, bringing them together to better understand their needs. And the same thing, if you're developing something for clinicians within a hospital, is you need to hear what they're saying, engage them in the process. And then if you do that, it's more likely they'll be adopted rather than just have a tool, bring it in. And then there's oftentimes resistance because they're not involved in the process. So I think it really ranges. And I think that's where, if we want AI to be effective, and I think avoid kind of what we were talking about with AI winters, is really need to be thoughtful about these things and really engage the range of stakeholders. And it's not even just, in the hospital setting, providers or patients. There's a lot of organizational issues that you have to think about. Every environment is different. The culture is different. And so there are many different factors that go into why something may work and why something may not work. And so that's where a lot of what the learning health system is. You can't just, there's many different factors. There's the health system level factors, there's patient factors, there's provider factors, the family. And these are all things need to be taken into consideration whenever you develop anything.
Thank you a lot. I'll try again. If there are any questions, we have a couple of minutes to answer them. Yes. So, okay, I guess you are not able to unmute yourself. So just a second. I try to do it.
I think it works.
Yes.
Does it work? Okay. So I have two questions. One, if you have a data set that you have generated, how do you know and what are the criteria to determine when to integrate AI approaches? We are doing some machine learning now, but when do we know that we are ready to integrate AI approaches into the data set?
Yeah, so I think there's a couple. I mean, I think there's if you want to think about putting in practice, I mean, there's multiple approaches, and I think there's a lot we can learn by others who are doing this. And so oftentimes I'm saying, let's find good examples that are out there. A lot of the ones I told you about are early on, but in an ideal world, before even looking at the data, is you have to know what problem. And I think there's one slide I had shown about, what's the task you're trying to achieve, and then who's the stakeholder, and even just ideally having a conversation, so there's different qualitative methods, whether it's interviews or focus groups, asking what is it that's needed, and not just developing a machine learning model in isolation. So in an ideal world is you kind of start with what's needed, talking to potential end users, and then saying, okay, what data do I need to actually answer that question? Then going and then finding those data, and then working closely, ideally, if your end user is a clinician or if they're a patient, working with them as you're developing it, thinking about things. I mean, there's also, as you go into data, you might say, oh, well, I think I can use this example, smoking status. So, you develop something, the model with smoking status, but in reality, as those data, it's getting better in terms of their collection, but there's a lot of data quality issues with things like smoking status and things trapped in notes. So if you were going to say, oh, well, I want to put it into practice, so at real time, I'm going to pull smoking status and all these different clinical variables, you have to kind of think about, well, it's actually hard to get certain variables like smoking status. And so kind of keeping that in mind as you're developing the models, and knowing like you might develop the model with a variable, if that variable is difficult to get at the point of care, then you won't be able to implement your model properly because you can't get that variable. So I think having some thought, and it's hard. I mean, I think there's different ways you can do it, but having some thought of how you could put it in practice, and that's why having interdisciplinary teams. So if you're working on a particular problem, say if it's in cardiology or mental health, having someone with expertise in that to say, well, that doesn't really make sense because if you develop that in practice, we can't really use that. And then, or say, oh, but this is a really important variable, and then kind of working together as a team. And so this is where I think having those interdisciplinary teams, really in team science, you have to have domain experts involved as you're doing the work. So hopefully that helped answer the question. I don't think I think this is a lot of things we're still learning, and different areas will have different ways of working, but.
All right. Yeah, no, in part, I think it's helpful at least to know that there are some important things. We obviously have the question we want to answer. So that's no, I just have to make sure that the variables, but it was more a question of, is there a specific size of the data that we have to achieve in order to start thinking about AI?
I think it varies. So there is this question comes a lot, is having 10 enough? Is 100 enough? I think I've tried, and others may have better answers, but I think we find, sometimes it depends on the question. It depends on the model. Some models need more data than others. I think I've found on sites, if you have 100, maybe it's fine. And sometimes it really just depends on the problem. And I think a lot of it is just you learn as you go. And then you try different things. I mean, there's all kinds of issues you'll run into as you're doing the modeling, class imbalance, things like that. And so there's a lot of things that go into consideration, and, sample size always comes up as, what's the N that you need?
That's very helpful to know that it can vary depending on the question. And I have a second question, and regards FDA approval, right? So if you, for example, are moving towards towards diagnostic, at the moment, are FDA guidelines clearly clear to understand how to implement it? What are the criteria to accept your solution when it comes from AI approaches?
Yeah. So, I mean, there's a thing, I think that gets to a lot of the regulatory. I mean, there's just a lot of things to keep in mind, not just the user, but things that we worry about, kind of the ethical issues, the regulatory issues, privacy and security. So there's just, I think the things is there's lots of opportunities, but lots of challenges, and there are many different things to think about. And I think that's part of it, is just as you kind of go into these projects, these are very large projects, and just being aware of all the things that need to be thought about that go into it. But these are things that those in the community are all working on that we can actually learn from.
All right, thanks.
So thank you again, Liz, for participating to this symposium. And if anyone has more questions, you can directly email and proceed with an offline conversation. So now, we are moving to our next speaker. And so I'm happy to present you Wu Tao. If you are there, you should be, let me say, just a second.
I'm here, yeah.
You're here, so, okay. Can you share the presentation?
No.
Okay, so I
think you need to make me co-host.
Okay.
Try to share it again, Wu-Tao.
Okay.
I just changed some permissions.
Yeah, I can do it now.
Perfect.
Can you see my slides?
Yes.
Okay. Let me just go into.
Okay, so while you adjust the screen, So I will introduce you. So Rotao is a PhD candidate in the Department of Biostatistics, and he is advised by Dr. Steingrimson and Dr. Gatsonis here at Brown University. He pursues research in machine learning and deep learning models with application to biomedical data. Before joining Brown, Rotao worked as a data scientist at China Resources. He studied in United Kingdom, where he got his master's degree in applied statistics from University of Oxford, and he got his bachelor in mathematics from the Imperial College of London. So I yield the floor to Rotao at this point.
Thanks, Christina. Thank you for introducing. And hello, everyone. Thank you for coming. My name is Rotao, and I'm currently a third-year PhD candidate from the Biostats department. Today, I will be introducing one of my research projects that focuses on identifying subgroups with differential prediction accuracy. This is joint work with my advisors, Dr. Steingrimson and Dr. Gatsonius. So I'll first talk a little bit about why we want to study this problem, the motivation, and also some related research in the literature, and also how our work is different from the existing methods. Then I'll introduce the main tree-based algorithm that we developed. And then I'll very briefly go over one or two examples of how to compute these estimators mu and variance of mu, which are like the key quantities used in the algorithm. And in the final section, I'll show you some of the preliminary results from our simulation study, and also the result that we got from after applying the method to the LLST data. So, sorry, I think this is mixed up. Okay. So the problem actually arises when we are evaluating the performance of a prediction model. So because when we evaluate a model, we often just look at the overall performance. For example, if we care about the area under the ROC curve or AUC, then if the model has high AUC on test data, then we sort of just say that the model works pretty well. But the problem is the overall AUC representative of all the subgroups? For example, it is reasonable to ask whether a model built on a predominantly white population would perform equally well for, say, African Americans. So the question that we want to ask is, for a given model, whether there is some subpopulation that the model is extremely effective at predicting, that's driving up the overall prediction accuracy. Or similarly, we also wish to know if there exist specific subgroups that have lower prediction accuracy. So these questions are very important for many applications because they provide us with a lot of insights into whether a model is fair or is it biased for certain subgroups. Here is another motivating example where the overall performance is kind of misleading. So here we are looking at the task of predicting whether a chest X-ray is indicative of a collapsed lung or not. So you can apply any standard deep convolutional neural networks, and it turns out that it's going to work pretty well. The overall AUC is 0.87. But if you take a closer look at what the algorithm is picking up on, then you sort of see this this thin tube here. So that's a chest drain, and it's a common treatment for a collapsed lung. So it turns out that these models, they're actually picking up signals such as chest drains when they're trying to predict whether someone has collapsed lung or not. And quantitatively, you see that the subgroup of untreated patients, they have much lower AUC, which is like 0.77, compared to the group of people who have been treated with chest drain, which has AUC 0.94. So in other words, the untreated patients, the people who probably needed the prediction the most, have much lower AUC. Or in other words, actually the model is predicting accurately on the patients who you already know have collapsed lung because you put a chest drain there. So it's very important to look into these kind of problems because they actually provide a lot of insight into what the model is actually doing. So many methods were developed for identifying subgroups with differential treatment effects in clinical trials data. And to the best of our knowledge, there's only one study in the literature that identifies its subgroups with enhanced prediction accuracy. But it was restricted to a specific kind of prediction model. And it also can only be applied to the specific data set that they were using. So in our work, we propose a tree-based algorithm that can work with any measure of prediction accuracy. And it's also model agnostic. So in other words, our algorithm can also work with any prediction model. So now I'm going to introduce the main algorithm. Before that, I need to introduce a few notations. So we have IID data. Xi is the p-dimensional covariate vector. Y is our response, which could be binary, 0, 1, or it could be a real number. And we define H hat to be the prediction model that is given to us, which maps the predictors X to the outcome or response Y. And we define W as a subgroup if it is a subset of the covariate space. And notationally, we define the prediction accuracy for a subgroup W as mu of W. So mu of W could be like mean squared error or AUC or Breyer score, basically any prediction performance that measure that you can think of. So to summarize, our goal here is that given a data set D and a prediction model H hat, we wish to see if there exists some subgroup that has different differential prediction accuracy. And the first step of our algorithm is actually to grow a very large initial tree. So what we do is we start with the root node with all the samples in our data set. Then we build the tree by first we pick a predictor xj and some cut point C, and we split the covariate space into two subgroups, L and R. So basically L contains all the samples that have xj less than C, and R contains all the samples that have xj greater than C. Then we compute the splitting statistics S, which is given here. S measures the standardized difference in the prediction accuracy between L and R. As we can see in the numerator, we have the prediction accuracy of the subgroup L minus the prediction accuracy of the subgroup R, then divided by the standardized error. So then once we have this, we just repeat this repeat these steps from A to C in order to find the predictor J and the corresponding cut point C that maximizes this difference, this standardized difference. And this would actually give us two subgroups, L and R. And then we repeat this whole step to the resulting two subgroups until we hit some pre-specified stopping condition. And then that's the final tree is what we return for the initial large tree T0. So the next step is to prune the tree because the large initial tree is probably overfitting and producing a lot of false positives in terms of identifying meaningful subgroups. So what we do is we define this split complexity of a tree, where the first term is the sum of all the values of the splitting statistics at each internal node of the tree. And then we subtract from it alpha times the number of internal nodes in the tree. So the norm of I sub t, it measures the size of the tree. And this is like a regularization term because we want the sum of the splitting statistics to be big, but to increase the sum, the algorithm will just keep splitting and produce a huge tree that doesn't really make much sense. So here we are penalizing its the size by this using this alpha times, sorry, the slide didn't go there, sorry. So we are using this alpha times the size of the tree as a penalization term to penalize large tree that doesn't make any sense. So here essentially this alpha S sub alpha t is it's like a measure of the trade-off between the goodness of fits and the number of splits. And alpha controls how much we wish to penalize for having additional nodes. So the way we prune the tree is kind of similar to the weakest link pruning in regular classification and regression tree. We just increase this alpha value and we'll end up with a sequence of subtrees because we can just sequentially remove the weakest link. Now, in order to select the best subtree, we use k-fold cross-validation. And in regular classification and regression trees, the value alpha is kind of chosen to minimize the k-fold cross-validated prediction error. So for example, in regression, we might be minimizing the sum of squares. However, in our case, the trees, they're built to distinguish observations with differential prediction accuracy. And these quantities they are not available at individual level. So we cannot simply compute some form of cross-validated error for each subtree and choose the one that minimizes it. So instead, what we do is we calculate the cross-validated split complexity for each alpha, and then we choose the alpha that gives the largest cross-validated split complexity. So that was a very brief introduction to the algorithm. And now I'm going to quickly go over some examples of how we compute these quantities, mu and the variance of mu, that are used in the calculation of the splitting statistic. So here, if we have a y response that is a subset of the real numbers, and we're using mean squared error as the prediction performance measure, then it's pretty easy to see that our mu is just the expected squared difference between the true response minus the predicted value. And it's pretty easy to find the unbiased and consistent estimator for mu, and also the unbiased and consistent estimator for the variance of mu. So this is like just standard calculation. And when we have a binary response with classification error rates as our performance measure, then mu is defined as the expected value of, so essentially it's just counting what's the proportion of cases that we are classifying incorrectly. So here mu is just the empirical estimator of that. It's pretty easy to show that it's also unbiased and consistent, and also the unbiased and consistent estimator of the variance of mu hat. So in the case of AUC, it is defined with this equation, and we can use the Mann-Whitney U statistic as an estimator of the AUC, and because it's a two-sample U statistic, so we can use the standard variance formula to find unbiased and consistent estimator of the variance. So essentially, you can do this for many other prediction performance measures that you can think of, like sensitivity, specificity, precision, or if you care about calibration, then you can also do this for calibration error or Brier score, or even loss-based measures such as negative log likelihood. So yeah, so that was a quick introduction to how we calculate these splitting statistics for different subgroups. So now I'm gonna present the preliminary results that we have from our simulation study, and also our application to the NLST data. So for the simulation, we have 6 covariates here. So x1 up to x4, they are just independent normal variables. X5 is Bernoulli with probability 0.5, and X6 is just a discrete variable with this PMF 0.1, 0.3, and 0.6. So we simulated 3 different scenarios. So in the first one, the true underlying data generating process is given by this formula, and the prediction model H hat is essentially the same as the true model. So in this case, if we apply our tree algorithm to this prediction model, then we should expect to see basically no splits from our tree algorithm, because there shouldn't be any subgroup that has differential prediction accuracy. And in the second case, the prediction model H hat is actually inconsistent with the true data generating process when x2 is positive or when x5 is 0. So here, if we apply our tree algorithm, then we expect to see different prediction performance between data with x2 greater than 0 and data with x2 less than 0, and similarly for x5. And finally, in the third case, we have a binary response, and we can see that the prediction model is only correct when x2 is positive or when x5 is 0. Otherwise, the model is incorrect, and the corresponding predictions should be poor. So now if we apply our tree algorithm to all 3 scenarios that I just described, each for 500 simulation runs, then we get the following results. So here we are using 4 different metrics to evaluate how effective our algorithm is. So the first metric is the proportion of trees that make a first split on the correct predictor. And the second metric is the proportion of trees that only splits on the correct variables. So essentially we're using these first 2 metrics to see if our algorithm is it focusing on the correct predictors to split. And for the third metric, it's the proportion of trees that has the correct number of splits. And the last one is the proportion of trees that have the correct depth. So these two metrics, they are looking at if the algorithm is splitting or making subgroups more than necessary, because we want to control overfitting. And we can see that our algorithm is working pretty well in general. So these 0.95, they are just essentially they're actually just showing us the significant level of our algorithm. So because if we look at the 5% significant level, then this is exactly showing that. So now, if we move on to a real data set and real prediction model. So here, with the data set we're using come from the National Lung Screening Trial. It has about 53,000 participants. And after we clean the data, about 49,000 are applicable for the prediction model that we are considering here, which is the PLCOM 2012 model. This model predicts lung cancer probability in 6 years. It comes from this paper, and it was developed using the control arm data from another cancer screening trial, the PLCO, hence the name. And so this is the prediction model that we'll be using. And the covariates, or the predictors that we consider for our tree algorithm include basic demographics like age, education, BMI, race, ethnicity, and also history, personal history of cancer, family history of cancer, and also smoking status, like smoking intensity, smoking durations. And if we apply our tree algorithm to this data set with this prediction model, then this is the tree that we got. So we can see that it has 2 splits, which results in 3 terminal nodes. So node 4, 5, and 3. So it only involves one predictor, smoke year, which measures the duration of smoking in years. And we can see the AUC of the prediction model evaluated on all the samples is 0.70. So this is node 1. That's all the samples in the data. And we can see there's a significant drop in the AUC from 0.7 to 0.6 when we only look at the subgroups of people who smoked more than 42.5 years. So that's node 3 and node 5. And we also notice that the AUC in all 3 subgroups, so 3, 4, 5, they are all smaller than the overall AUC. So one possible explanation is that the covariate smoke year is an important predictor for lung cancer probability. And we have so when we have a population that has a wide range of smoke year values, the prediction model can predict reasonably good because it has AUC of 0.7. However, when we only look at the subpopulation with longer than 42.5 years of smoking history, then the model starts to have trouble distinguishing who have relatively high probabilities for lung cancer and who do not. So which is reflected in the decrease in AUC to around 0.6. So in other words, the model is kind of relying on the predictor smoke year to see who has higher or lower probabilities of lung cancer, which is not surprising because if you ask me, I'd definitely base my predictions on this particular variable. But it does make you wonder how good this prediction model really is, because if you only give the model people who smoke more than 42 years, then the best AUC it has is only 0.6. So this is kind of an interesting result to find out. So this is also showing that the overall AUC of 0.7 is somewhat misleading. So these are the preliminary results that analysis that we did, and we are still working on the evaluation of our algorithm. For example, we are considering having more complex data structure for the simulation study, and also for the NLST data, we are looking at extending the set of predictors that we consider, and also what kind of possible effects there might be if we split on important predictors such as smoke year or other important predictors in the model. So this concludes my talk today, and thank you for listening. And I'm happy to take any questions that you may have.
Thank you, Rotao. Are there any questions? Also think that I change my view. Okay. So if there are no questions, I wanted to ask you if the model, other than showing us that there are some problems recognizing subgroups, is also trained to actually, is optimized in such a way that we are able to find a model that works properly for many of these subgroups.
Sorry, could you repeat the last sentence? I think the connection is a little.
Okay, yeah, my question is, with this model, we're able to understand that depending on how the tree splits the attributes that we are training the model on, we are actually able to recognize that some predictors can be representative for part of the population and may not be so valuable for other parts of the population. Is it right? Am I right up to this point?
Yeah, because I think we're not actually trying to find the predictors that, yeah, in a way, yes, we're trying to find the variable that if we split on this variable, then the resulting subgroups have differential prediction accuracy. Yes, that's basically what we're doing. So essentially what the problem that we want to answer is that we have these different prediction models and they are reporting, AUCs as an overall measure rather than what kind of performance you have on certain subgroups. So we want to see if these models are actually performing equally well in different subgroups. And the tree algorithm that we build is actually trying to see if we can actually find those subgroups that have differential prediction accuracies.
Okay, so the final goal is to build an algorithm that is able to give me prediction that work properly homogeneously on the entire set, independently of the subpopulation that we are taking into account.
We're not really actually trying to modify the prediction model. We're considered that prediction model is fixed and a given. So we're just trying to see if this prediction model is actually representative of all the subpopulations. So
Great.
Yeah, so that's essentially what we're doing.
Yeah, that's very interesting. There is a question. Shazad, can you unmute yourself?
Yes, I can.
Okay.
So when you were showing your analysis on the examples, the simulations you had, you mentioned you are analyzing the depth of the tree and the number of splits, and you compare it with actual what you expected. First, how do you obtain like the actual number of the splits and the depth of the tree, and you do this comparison? And second, what is the significance of the depth of this tree?
I think because in the simulation study where we had these where we had this setup where we know what the subgroup should be. So in the optimal situation, we know what kind of tree that we're expecting. So for example, if in one of the simulation scenario we had cases where x2 is positive and also where x5 is 0, those are the subgroups that are having trouble with the prediction model. So so we are expecting the trees to only split on these two covariates and only split them once. So that's how we come up with the correct number of depths and the correct number of splits, because we know the subgroups.
So one other question, if you know if you have some idea, so let's say you know that there is a group that your model is not really representative for that group. You know it's one group, or you know there are two groups. Then do you still have to do this branching algorithm for the trees, or you can just obtain it easier? Because that you would have an idea what is the shape of this tree.
Well, because in the simulation case we do, but like in the real case that we don't really know what the trees would look like. So so we don't really have an idea of the real depth of the tree or the number of splits that we should be expecting. So as you can see in our NLST example, we had 2 splits which are actually all splitting on the same predictor, which might not be optimal, but I think we're still working on that to see how we can control that kind of behavior. But I guess, yeah, does that answer a question?
Yeah, kind of. Thank you.
No problem.
Are there any other questions? Okay, so thank you again, Rotal, for your talk. And so we close this first day of the symposium, and we'll meet again on Friday, 29th January at 11:30. And you can find the link on the website. You find also this event. So we hope to see you all